Set of lectures now. We've not heard from you before, but jointly given by Guido Lombardi and Jean-Michel Bernard. So Guido works at Politecnico di Torino and Jean-Michel Bernard at the SIREV in France. And the whole title would interest many of you that have played with diffraction problems and its links between Wiener Hopf and Sommerfeld type integral methods, which, well, sounds like a very interesting topic. So please.
Thank you, Raphael, for the presentations. I would like to include that Professor Guido Daniele from Politecnico Torino is also involved in discussion between me and Professor Bernard. My background with Professor Daniele is engineering, and the background of Professor Bernard is mathematicians, famous mathematicians. So we think that shared knowledge of interest in applied mathematics is an important thing, and we have probably different views and different rigorous mathematics in these slides, and we hope this material is of help for everybody here. The interest on trying to find a link between Wiener Hopf and Sommerfeld Malyuzhinets technique dates back to a sentence of Keller, that everybody knows Keller in Diffractions. In particular, he thinks that the methods are different, but they are closely related. And we try to, with these lectures, to find these differences and similarity between the two methods. In particular, in the paper of Keller of 1979, he made the question, what feature of the methods account for this difference? And find the difference is an important thing, but probably the relation between the two methods are even more important. And the second sentence is, it might be helpful to understand this in order to predict the success of the other methods. So the difference and similarity can help solutions in both methods. We agree with this sentence. In particular, we think that if we apply Sommerfeld Malyuzhinets technique and the Wiener Hopf technique to the same problems, we can find some synergy between the two methods. Some properties of the one method can help the other, and vice versa. And in the past, the Sommerfeld Malyuzhinets method and the Wiener Hopf techniques were considered disconnected, different between each other, in particular because the Sommerfeld Malyuzhinets technique was defined an angular complex representation, while the Wiener Hopf technique was defined in Laplace domain unilateral Fourier transform, or using Fourier transform. Okay. So the aim of the course is to find significant point of similarities, and we found, in particular for new canonical problems, and even in wedge problems, that both methods are very similar if they are expressed in similar equations, like in terms of difference equations. However, the two methods find effective solutions using strongly different solution procedure. However, all these properties and similarity, diversity, can help the progress of prospect in the theory of linear waves propagation as told by Keller. Here is a novel canonical problem with both methods. I had a discussion with Professor Speck about what is canonical, and probably he can report some good definition for saying what's canonical. Here we think that this is a kind of novel canonical problems, is a polygonal structures, and this will be presented in the last lectures as an advanced topic on these lectures, list of lectures. The efficacy studying complex problem can be done with generalized version of Wiener Hopf and generalized version of Sommerfeld Malyuzhinets that are effective to study wedge problems, but we can go beyond, and we will treat about the three-part polygon, starting from here is an impenetrable structures. Here I have reported PEC means Dirichlet boundary conditions. My terminology will be electromagnetics because my background is electromagnetics. So sorry for referencing just from these few slides to terminology in electromagnetics, but I will use that. In E-polarization, PEC means Dirichlet boundary condition. Okay. Recent progress in both methods. In Sommerfeld Malyuzhinets technique, Professor Bernard is here and will talk in the second lecture. One of the main progress is that he can find a functional difference equation in Sommerfeld Malyuzhinets technique without the use of Malyuzhinets inversion theorem. This is a nice progress in the technique. And one of the main progress that we consider in Wiener Hopf technique is the reductions of Wiener Hopf equation into integral equation for their effective solutions. And we will show some simple application in the first lecture. The first lecture will be given by me, and I will talk about Wiener Hopf equations and transformation to integral equations. Lecture 2 will be about Sommerfeld Malyuzhinets technique tomorrow morning. Then we will have a lecture 3 that we share time between Professor Bernard and me. We will handle with wedge problems in both techniques, Sommerfeld Malyuzhinets and generalized Wiener Hopf equations. Then lecture 4 is devoted to the new novel canonical problem, starting from perfect electric boundary conditions, impenetrable wedge, and then going to surface impedance generalization. Okay, this is the introductions, so I switch to the first lecture. Okay, so the first lecture is about the Wiener Hopf equations and their transformations to integral equations, and this material is in collaboration with Professor Daniele, has told before. The summary of the presentation is that we have classical Wiener Hopf equation in spectral domain. We will have generalized version. Then we will present what we call freedom factorization. We will present an unusual way to solve Wiener Hopf equations when, especially when a closed form solution of Wiener Hopf equation is not available. This method will be effective, and we will show the solution procedure. The main reference to these first lectures are the paper that we wrote in 2007 in Radio Science, that is about mathematical applications, simple kernels that we factorize, and we find solutions of simple problems in electromagnetics in using the freedom factorization. And another reference, important reference, is the book by Professor Daniele, published in 2014. So let's start from the beginning. First of all, the engineering assumptions for the complex variable, the imaginary, is J, so I will use in this slide J instead of I. Sorry for this difference. So we'll use this symbol, and it's equivalent to I, and all the definition will be related to the classical that we have seen in previous presentations. And starting from the very beginning, here you have a convolutional equations. We can find a solution of convolutional equation easily by applying Fourier transform and inverting the kernel, and then we get solutions. Wiener Hopf equations are semi-convolutional equations, so we have an integration path from 0 to plus infinity here, and the source term, and this equation is in the interval 0 to infinity. We can rephrase this problem into this one. We have seen these equations, these kind of manipulations in previous presentations, and now we have an integration from minus infinity to plus infinities. U is unit step functions, the if side functions, Then we have the sources here with the unit step functions. Then we have f minus here. If we apply Fourier transform to this equation in physical domain, we get an equation in a spectral domain using Fourier transform, where we have G alpha is the kernel of f plus, f minus, and the source. Okay, so we have this kind of bilateral Laplace transform or Fourier transform applied to f plus. We can rephrase these into Laplace transforms as done here, this engineering notation probably, with J. And then we have the Manes functions. We have properties of regularity properties of the unknown. The plus function converge, it means it's regular in the upper half plane, and the upper half plane is defined here with half up, and the Manes functions are regular in the lower half plane, reported here. We call non-standard, non-conventional plus and minus functions when we have half AUP, the imaginary part of this that is greater than 0, or in case of minus function when the imaginary part of half LO is less than 0. So we have singularities on the upper half plane, on the lower half plane, but the functions goes to 0 in the upper plane and the lower plane. So we start with an assumption. In my background is wave propagation in electromagnetics, so we consider propagation constant with negative vanishing imaginary part to avoid singularities in the real axis. And we can have this kind of equations that is inhomogeneous. We can rephrase the problem also in a homogeneous form here, where we have defined the Manes functions as this. If you see this can be the source in wave propagation can be a plane wave incident in scattering objects, and can have singularities like geometric optic poles, and they can be in the regularity plane of the Manes function. So f minus can be, it depends on the incidence directions, can be a non-standard, non-conventional Manes functions. Okay, here is some synthetic view of this classical method to get a solution. The equation can be in general in matrix form, and first we have to highlight the kind of unknown. We have a plus unknown, minus unknown, a source term here, and using a specialized technique in classical Wiener Hopf technique, we can have the multiplying factorization. So we split in G the kernel, in G minus, G plus, and these techniques are possible in closed form only in particular cases. We will show how the freedom factorization can handle more types of kernels, especially when you don't have closed form factorizations. And by splitting the kernel, then we can rephrase this equation into this equation. We invert the G minus, and by using what we call decomposition, probably this is a multiplying factorization, this is an additive factorization in terminology. Decomposition is the additive factorization. We split this term that is a terms that is not minus, not plus into the minus and plus. So we decompose this in minus plus in additive form, and taking the minus and the plus form to one side, to the other side, then we have here plus equations. Here we have a minus equations. Thus it can be equal to an entire function. If in particular for scattering problems in electromagnetics, you can formalize this in such a way that the entire functions usually goes to 0. So we can apply the Liouville theorem here and get the solution directly by solving this equation, and this equation equated to 0. And here is the solution in closed form when we have this possibility in terms of plus functions and minus functions. So we want to focus that this procedure is the classical one, and it's possible when we get the factorization of kernel and the decompositions of this function. Okay, here is the same topic but applied to the homogeneous equations. In this case, one of these unknown contains some non-standard singularities due to the sources. So F plus or F minus contains some singularities that stay in the classical regular half plane, upper half plane for the plus function, lower half plane for the minus functions. First of all, we factorize the kernel, we move the minus portion of the kernel to the right hand side. Then here we think about our wave problems. So we think that the non-standard poles of F plus, F minus are due to the sources, like incident field. So we were thinking here to have more than one waves in case of a kind of incident. So you have non-standard poles that stay in the upper plane or in the lower plane. So here we have reported that alpha 0 and beta 0 are poles due to the sources that stay in the standard half plane of. So F plus possesses a first order non-conventional pole at minus beta 0. So minus beta 0 is in the upper plane. F minus possesses a first order non-conventional pole in alpha 0. Alpha 0 is in the lower half plane. So from here we extract this kind of poles that is non-standard. We make the composition, and as done in non-homogeneous Wiener Hopf equation, now we have a left-hand side that is plus equations, the right-hand side is minus equations equal to an entire functions, and also in this case we think that the entire function goes to 0 because of the properties of electromagnetic scatterings, and thus we get the solutions reported here for the plus functions and the minus functions in terms of the sources. T and R are excitation sources, so they can be excitation of geometrical optics in wave scattering. Okay. Also in this case, I want to show that to get
so basically this is like pole removal, right?
Pole, yes.
Pole removal, huh?
Yes. And also in this case, these classical solutions are obtainable only when we have closed form of factorization of kernels and decomposition. Okay, here I'm presenting some integral properties of decomposition. These are the classical Cauchy decomposition formula. If you have a spectral functions like f, you can get the plus portion using contour integration. This is called the smile contour. This is called the front contour. The smile contour allows to get the plus portion of f. The front contour f minus get the f minus, the minus portion of f. The smile contour is reported here is the real axis gamma 1 with a small semicircle around the observation point alpha, okay, and the front contour is reported here is we call gamma 1 the small contour, gamma 2 the front contour is the real axis is with a small semicircle in the upper plane around the observation point. So this is the notation used. gamma 1, gamma 2, and we have this kind of representation in terms of semi-residue and principal value integrations reported here when we have the alpha is with imaginary part equal to 0. Other properties. Here we have some properties that we are currently use to get freedom factorization. In particular, we have some modified Cauchy decomposition in case of non-standard functions. So in this case, we consider that plus functions and minus functions are non-standard functions, non-standard plus, non-standard minus. It means they have some source, some pole that stay in the regularity half plane. In case of plus functions is in the upper plane, in the case of minus functions is in the lower half plane. We call these portions F plus and S non-standard, or in the case of minus function F minus and S. So if we apply the Smile contour to the F plus that is non-standard functions, can be standard, okay, but in case of standard functions, we have the trivial equality equal just the F plus functions. And in case of non-standard functions, you get these extra terms. The non-standard portion is reported here. If we apply the gamma 2 to F plus, we get only the non-standard portion. If we apply the front contour to the minus functions, we get the minus functions with sign due to the closure of the contour. These properties are obtained by closing the contour in the regularity half plane. In the case of F plus, we close the contour with infinite semicircle on top. In the case of minus, we close this on the bottom. And we get for the minus functions with inverted sign due to the orientation of the contour integration, and then we get the extra term due to non-standard singularities of the minus functions. If we apply finally gamma 1 to minus functions, we get directly the non-standard portion of minus functions. Okay? If you have a standard functions here, you get 0. That is clear, because you don't have any singularity here. Okay, we will use these properties to get the freedom factorization of the integral representation of Wiener Hopf equations in the following slides. But yes?
So, yeah, it's confusing your notation. So how are we meant to know when we have one of your non-standard plus or minus functions?
Okay. What? Can you repeat the question?
So how do we know if you have a non-standard?
Okay, that's true. Good questions. Yes. In our application, usually you know about geometric optic solutions in advance before taking the solutions of complete diffraction problems. So you can study in advance the geometric optic solution. Geometric optics have infinite supports. In that case, infinite supports give you the pole of your problems. So you know in advance that your spectral solution F plus and F minus contain poles, just studying geometrical optics of the problems in wave scattering. Okay?
So do you know the position of the pole?
Yes, we know the position of the poles because you can study using classical geometrical optics the problem in advance. Okay? Okay?
So wouldn't it be the same as just adding a forcing term?
Forcing term, yes, it is the same.
You can extract
Yes,
it out.
you can extract out, and that is the forcing term. Yes, that's the
Why is it
homogeneous or non-homogeneous versions of the Wiener Hopf equations. It's like that. Okay. Okay. Here I'm reporting before starting with freedom factorization some slides about factorizations of kernels. Here is a classical topic of logarithmic decomposition. starting from scalar kernels, we can rephrase the kernel into exponential form with logarithm here by using decomposition formula like the Cauchy decomposition formula done before you get the factorization in terms of exponentials. We can apply easily this technique to scalar kernel, but we can generalize to matrix kernels when the matrices G minus and G plus commute between each other. Okay, and this property is not just for Wiener Hopf matrices, but is a general mathematical properties. Here we have some slides about the matrix factorization, and of course these topics in closed form is very interesting. There is a very good papers. It's a sector that in Wiener Hopf have given a cult activity for many scientists, and we need that to solve Wiener Hopf vector equations. But Wiener Hopf vector equations are solvable only in very few cases when you have special properties. So there are papers that report constraints on how to find factorization in closed form for matrices. And the book of Professor Daniele here reports is a wide literature to have this closed form of matrix factorization. In particular, below I report the matrix factorization of order 2 in the case of Daniele Krapkov factorization, and this is when the matrix commute with polynomial matrices. Here is the form of Daniele Krapkov matrices, where A and B, when you make the division A over B, you get polynomials and polynomial P. In these cases, you can get a closed form factorization, and here are reported the equation to get the closed form factorization. Here we have the definitions of G, small g, that is the scalar factorization of determinant of the matrix G, and here we have a function T that is decomposed in T minus, T plus, and the final solutions for getting the G plus is reported here, and the book of Professor Daniele reports all the details on this kind of matrix factorizations. This topic can be generalized to matrices of arbitrary order when the matrices commute with polynomial matrices. In this case, we have an extra problems. It come out that in the middle of the procedure you get essential singularity behavior at infinity, and the book of Professor Daniele report how to handle this kind of essential singularity with a procedure that is not reported here, and to eliminate such essential singularity. Okay. Remark here that Wiener Hopf factorization for arbitrary matrix in closed form is still a challenging problem, and of course there are constraints. Not all matrices can be factorized in closed forms, and what we want to highlight here that in the next slides I will report the freedom factorization that is very flexible, so can be used is an approximated, of course, approximated factorization, but is very flexible. You can get factorization for problems, then you can modify the parameters of your problem, get another factorization with similar procedure, and so it's practical to be used and to get solutions of problems. The proposed method that we have used in solving electromagnetic scattering problems is reported here. We first of all, we get the Wiener Hopf equations. Here is reported also the keyword GWHE, that is generalized Wiener Hopf equations. So we call that generalized in particular for angular region problems when you have wedge problems, because in that cases the minus and the plus function we have different complex variables, but they are related together. So it's not like a two variable as Raphael presented, but they are related together. So we can do some trick to get classical Wiener Hopf equation. Then we apply what we will show, the freedom factorization to the Wiener Hopf equations. Then, after that, we get approximation of the spectra, the plus unknown and the minus unknown. We need the analytical continuation. The discretization procedure define the solution in proper sheets or in a portion of the complex plane, and so you need some procedure to get analytical extension of the spectra. Then after that we usually do asymptotics to get physical engineering parameters like total fields, geometric optic fields, diffraction fields, and so on. Here is an asterisk there, possibly with the help of equivalent network modeling. My background is electromagnetics. We have a reference book that is Feltz and Markowitz's book on wave propagations. They use strongly network modeling to represent mathematical equations. Of course, mathematical equations can stay by itself. They are well defined, clear, but when we start to compose complex problems constituted by different portion of canonical structure, if we have a pictorial view of the problem in terms of circuits, where each portion of the circuits is a mathematical equation, then it's easy to compose more complex problems. So that's why here I'm reporting that the equation involved in this procedure can be rephrased in terms of network modeling. The method is flexible. We can apply to wave scattering kernels. The solution is approximate, but how we write the equations contains all the spectral properties of the physical problem. So when we get to the solution, we don't use in the integral equation very refined quadrature techniques, very refined numerical techniques to solve the problems, but we use a quasi-analytical solution. It means that we use very rough technique because we have all the spectral contained in the formulation. So we will use in our solution very rough numerical technique like sample and hold, truncating the interval, and so on. So step functions to represent our solutions. And we can see inside of the integral representation all the singularities of the problems. If the problems contain poles like for geometrical optic components, for surface waves, leaky waves with branches, then we can see inside of the integral representation these kind of branches. So when we rebuild the solution in approximate fashion, then we can see all these poles, singularities of the spectral and get, using asymptotics, the components. The modeling, I thought the modeling is for a small portion of the problem where the structure is canonical, for example, angular regions, layers, and so on, waveguides. We have at the end of the procedure an integral equations that we call freedom integral equation. Most of our equations are freedom kind. We have all the problems. So even if the problem is composed by different canonical structures, all the integral equations, the vector integral equations, contains all the informations of the entire problem. So we are doing no iterative method to take into account near field interaction among canonical structures. Like if you have a double wedge problems, you get the formulations that contains all the problems, not just one edge, the other edge, and then you interact between them. Okay, let's start from what we call freedom factorization. So here is the inhomogeneous Wiener Hopf equations, and at the end of the slide we get these equations. We believe in that in most cases the kernel of these equations is compact, and the equation is of freedom kind, so or second kind. And the procedure from here to here is obtained using the contour properties that we have shown at the beginning of the presentations. And the aim is to eliminate one of the unknown, the plus or the minus unknown, by contour integration and get finally the freedom integral equations. In this case, from here to here, we have eliminated the minus functions. So we get these integral equations where we have only the plus unknown. Here is the kernel of freedom integral equations that is related to the properties of the Wiener Hopf kernel at the beginning. And what I was saying just before is that the properties of the solutions in terms of spectral singularities is contained here. So here you have all the singularities of branches, poles, and so on. So it's a formulation that contains all the spectra of the problem. So let's see how to obtain the freedom integral equation starting from the inhomogeneous Wiener Hopf equations. Here is a quite dense slide, but the procedure is quite standard. You have these equations. First of all, we try to eliminate the minus unknown. To do that, we perform the smile contour applied to the entire equations. Here is reported the application of the smile contour here. Of course, we have here the source term outside, so we have f minus, f plus are standard functions. So when we apply gamma 1, in this case, we obtain these terms where we have only just this. This is cancelled because it's a minus function is regular in the lower plane, okay? And then we have the residue of the source. So we get this. This is an equation that is in f plus, but we want to regularize these equations. To do this, we use the following property. First of all, we expand this integral along gamma 1 using the Cauchy formula reported before in terms of alpha residue and the principal value. So we get this. Then we apply gamma 2, so the front contour, to f plus, and we rephrase this integration to a principal value applied to f plus and with a semi-residue. Of course, it's regular in this case in the upper half plane, so it's equal to 0. So we subtract, we substitute this into this equation, and we subtract these terms, and we get finally this representation. That is the representation reported in the slide before. Okay, and we think that these kernels, using physical properties, is compact, and this is a freedom integral equation of second kind. Okay, let's start with, let's go back. We know that in with scatterings, when you have an illumination of the problem with wave fields, then with planar waves, we have f0 plus that is a simple pole, simple pole functions. Simple pole functions can be in the lower half plane or in the upper half plane, depends on on the incident angle. So here we report the equations for done before in the three cases when the poles, the source, is in the lower plane, in the upper plane, or in the real axis. So we have these three differences equations. It depends on the location of the pole of the source. Practically, we use the first two, not the third one, because it's the case where the third one when we have no losses in the problem, but we usually assume that we have some losses, so the geometric optic poles do not stay in the real axis. Okay, we want the solution of this equation. This is the case where the poles stay in the lower plane, and due to the properties of the kernels, the original kernel G of the Wiener Hopf equation, we have some singularities of our kernel. Can be branch point due to the propagation constant, can be poles of structures like layers, grounded layers, that can be surface waves and so on. So if we study the properties of the kernel, we see that usually singularities are located in the second quarter and then the fourth quarter. So we can solve the equation using the real axis, but because of concentration of singularities near the real axis in this position can be also branch cut due to the propagation constants. So we have applied contour warping. So we modify the real axis to some contour that goes further from the singularities. Why? Because in this case, the kernel, this kernel of the integral equation is more smooth, and we can solve the freedom integral equation with a more rough technique, because the kernel is smooth and we get a more nice behavior for the solutions. But the equation is valid also, is valid in the real axis. So if you want to apply the technique in the real axis, you can do it. Okay, here are reported some kind of contour warping. Here, this is the first one. This is another one. This is one that we often use. In particular, we can use this also not just for the bisectrix on the first quadrant for pi over 4, but we can also go very close to the imaginary axis, and we can do that, and we will show some results that where we do that in wedge problems. And in case of staggered structures, there is a paper of David in inverted half planes, and we have reproposed the same problem in electromagnetics and wave motion. The staggered allow to warp the line to an axis that to a tilted angle, that there is a constraint for the staggering of the structures, because the staggering of structure give in your kernel some exponential factors, okay? And then here we have another contour warping that, of course, also this skip the closeness to of singularities in the second and the fourth quadrant, can be in particular the propagation constant, and here we have another fourth contour warping. All these contours can be applied. This is really effective, especially when we generalize to an arbitrary tilted angle here. Okay, so here is a change of variable to do contour warping, and this is the same equations reported here after contour warping. Okay, let's apply the numerical quadrature to this. As told, M is well behaved and smooth, especially after contour warping. So usually to get solution, we apply what we call sample and hold by truncating the interval. So we truncate the interval minus a. So we are particularly interested in far field. So the spectral of interest is concentrated near 0. So for that reason. So we do that, but we are still thinking about near field asymptotic solutions. So in this case, I'm truncating the interval. H is the step of the integrations, and we, after performing the discretization, we get this. This is a 2a over h plus 1 times 2a over h plus 1 linear system. We can solve and get the sample of f plus. By using this formula, we rebuild our f plus, and we can analytically extend. You see here there is m, that is its dependence is on alpha, and this dependence on alpha contains all the spectral singularities of the problem, so branch cut, poles, and so on. Here is the same solution for f minus, and this is the definition of what's m. M is reported here. So let's see about a problem. This is the first case problem that I'm proposing. The problem is a radiation of a truncated planar waveguide. The waveguide is a perfect electric conducting, so it's impenetrable. We excite this problem with a T1 mode, so the first mode propagating inside the planar waveguide. Okay, so this mode is propagating this. This is the truncation. See, this is open space. If you formulate these problems using electromagnetic fields and so on, you get finally that the kernels contain this scalar kernel. The scalar kernel that you see here is a reported physical parameter. This is the angular frequency. Here you have the spectral propagation constant. The alpha is the spectral variable, so you have branch points here, and then you have this cosine function. D is the distance between the top and the bottom of the waveguide, and then you have these exponential terms. We can normalize normalize the kernel with these terms, so we know this the factorization of these terms in closed form. And here is reported the kernel without these terms. We need to factorize this, and the equation is reported here, where we have an excitation alpha 0 that is, in this case, the modal field, the first mode of the waveguide. If you look to the singularities of these problems, you get this picture where you have poles here due to these terms, and then you have branch points here and here. This is the kernel spectrum. So that's why we used to make contour warping, because in freedom integration you integrate here, so by contour warping you are going further, and you have a smoother kernel. Okay, let's see. First of all, I give a closed form solution for these problems. It's reported by Daniele book here, and we use in this case Mitter-Leffler to handle the cosine function. Then we have these terms to be factorized, and we have a closed form factorization of these terms. We assume that also here we have small losses in the problems to avoid singularities on the real axis. And after applying Mitter-Leffler and the procedure, we get this kind of factorized kernel, the G+. Gamma is the gamma functions, then you have some other terms here, the products, and there are some constant. Gamma is the Euler constant, and this is G+. If we get G+ small using the factorization of this enclosed form. Okay, finally, with these parameters, we get the solution of f plus in a standard way here, when we have alpha 0 that is in the lower of plane, and we get this solution. This is the closed form solution. Here is the solution that we perform using the freedom factorization to check the validity of the method. In particular, we have these equations. In this case, in this slide, I'm showing the picture of the kernel in two variables, x and y, okay, after performing contour warping and without contour warping. If you do not perform contour warping, you get this. So you have a very singular shape of the kernel near the branch points. The branch points, recall, they are here, here and here. Instead, if you perform contour warping like this or this, you get this kind of M behavior in x and y. So the shape of the kernel is much smoother, and when you want to solve this equation by simple discretization, this is possible with smooth kernel, but it's quite rough in using the real axis. Okay, approximate results. We have this equation that is a linear systems, as told before, is 2a over pi over h plus 1 times the same dimensions. We get a sample of f plus, and we can rebuild the solution using this formula. And this can be in this case, because it's rectangular shaped problems, we get the solution for all the proper sheet of the problems. So the proper sheet is defined by these terms. Okay. Okay. So let's go to the pictures. Now, we have to compare this solution with this solution in closed form using Mittag-Leffler. We used here a quite rough technique. A equal 40 is the truncation of the integration, and h is the step of the integrations. And if we look to the solution, in case of Mittag-Leffler, you have the solid gray line reported here. Okay, and for f plus alpha from minus 10 to 10. Then if we perform the solution using contour 1 is without contour warping. You get this, so not good. But if you make contour warping, you have the star and the circle here. I recall what's this kind of contour warping. This is a contour 1, no, the real axis. This is contour deformed like this, and this is contour 3. Okay, so you see, if you go far away from the branches, you get good solutions. And here you see that the Mittag-Leffler solution and the freedom integral equation with contour warping, you get overlaps of the. Here is reported the relative error between the Mittag-Leffler solution and the solution obtained by the freedom integral equations with contour warping 2 and 3, and you see that you get good convergence. Here you have the relative error when you study the relative error on the contour. So in this case, you compare this solution and this solution along the path of the contour warping. In this case, obviously you get better solutions because you have solved approximately your problems along a contour, so the solution is better.
How much is that?
Yes?
So what's more important, is it the value of A or the value of H?
Depends on the problems. So depends on the problem.
They should, in principle, all these integrals are the same thing, right? So if you compute them accurately, they should give you the same result.
You need some experience because to get the proper value of a and h. Okay. Usually I make self-convergence and comparing with completely different methods. Usually I compare my solutions with the finite element method to check if I get the same solution. So what I'm doing is that. Typical parameters are like you saw here. These are not well refined, but the scaling between h and a is typical. So 40 over 0.2 is it's kind that you can get good solution in terms of how many points. Start from that. How many points? In this case, 200, 300 points. It's enough. It's enough. Then you can check what's the right value of a. Look into the shape of the kernel. You have the shape of the kernel. So you see that it's going down here. So the tails are counting less. So you can truncate here. You see minus 20 to 20. So that's why we got minus 40 and 40. So if you look according to the contour warping, if you look to the shape of the kernel, then you can suggest the proper truncation. And also, the h parameter can be fixed looking to how sharp is the kernel shape. Okay.
Can I just comment also about you're comparing it against the exact solution?
Yes.
Your exact solution is solved approximately because you have to truncate.
Yes, that's true. That's true. That's true. You're right. You're right. Yes, we got a number. In this case, I think we got 200 terms. You're right.
I think these days it's quicker to use a Cauchy integral representation and it's more accurate than a truncating.
Okay, truncating that. Okay.
So what you call an exact representation is arbitrary.
Okay.
Yeah.
Yes, in this case we truncated that to 200 terms. That's right. And we saw that increasing the terms, we don't have we have a stable solution in this case. Okay. Okay, let's go back to here. So here was a scalar problem. Let's go to the matrix problem. Here is a problem that is a mathematical problem, is not related to a physical one. We have a G that is this kernel with parameters Q, B, A. Then we have R that is the excitation coefficients. Here is reported what's R. R is a vector. This is the basis of the vector. We have this kind of excitation. So the width of the first component is more than the second one. Then we have tested the solution for different singularities. One in the singularity excitation, one in the lower plane, one in the upper plane. These are the parameters selected for the test. Okay, we have a classical factorization reported here, and we get the solution in enclosed form when we have this is a real closed form, and with imaginary part of half zero in the lower plane, here in the upper half plane. So let's check the comparison. In this slide, I present the comparison between this closed form solution and these freedom integral equation solutions, and here we didn't perform any contour warping, and the solution is reported here for the first component and the second components of F plus, and you see that they overlap. No contour warping is applied here. Same discretization of before in this case. Here we make a check on relative errors for the poles on the upper plane, in the lower plane and the upper plane, and we see similar relative errors for the two cases. So we are comparing these formulas and these formulas for the discretization of freedom integral equations with these parameters. And here is another example, the other one, with alpha 0 is equal to 1 plus j, and we have the absolute value reported here for the first components and the second components, and the relative error. So you see that is almost 1% of errors. And what else? Here is a 3 by 3 matrix kernel. The kernel is reported here. We have reported the pole location of determinant of G and its inverse reported here in black and gray dots. In this case we have a source that is with a pole of minus J2 and with excitation of with the basis R, with the first component different from 0, and we compare these. Here is are reported the solution for no warping. The quality in absolute values are good, but we have some sharp behavior due to the presence of singularities near the real axis. So the relative error you see that are local error that bump, but if you make a contour warping you skip this, and this is a relative error along the contour warp. Here is another topic. I think I have some minutes. It's only some minutes. Okay, only some minutes. This is a minus 4. Minus 4. It's good. Okay, this is another application. I try to present this very quickly. I'm interested in this. This is you see that with freedom factorization we got the solution f plus or f minus, but probably we are interested in kernel factorization. So here is reported a way to get directly kernel factorizations using freedom integral equations. We create the problems. The problem is here. We have G alpha with uy plus and uy minus, and these are not Laplace transform, but if we put alpha on the bottom we get that goes to 0 at infinity, and we want to have n independent terms like this, and if we get n independent terms here, you can get the factorization using these two formulas. These come from the book of 1976, okay. And what we do is here we use auxiliary Laplace transforms in this case. So we define according to ui plus, we define this xi plus with a fake pole, alpha with p is a pole that we include in the formulations that is not belonging to the null space of G of the kernel and its inverse. That is important to avoid cancellations. So once we have done this, we can rephrase the problem into these equations, and if we impose that ui minus are the canonical basis on Rn, then we get n independent solutions. So we perform the classical solution if it is in closed form, but if it's not available, then we apply freedom integral equation, freedom factorization to these equations. And using freedom factorization, this equation is similar to this one, we get a solution in terms of ui plus. Ui plus is related to xi plus. So finally, when we get xi plus, then we rebuild ui plus. We can build ui minus and using this formula, you get the factorization of the kernel. And there is a question. There is a dependence on the selection of alpha p to get the factorization. And we can demonstrate that according to the selection of the pole alpha p that used in the procedure, we get different factorization of the matrix according to a matrix constant, a constant matrix, and the constant matrix is reported here. You can demonstrate by identity. So let's apply this to the kernel of a second example with a 2x2 matrix kernel. And here I recall the kernel of the second example with 2x2 kernels. And after the procedure, you can get the constant matrix K by comparing the exact solution here with the freedom integral equation solutions by checking these in one point. For example, alpha equal the origins of the alpha plane. And here is reported the K and the conversion of the Kg plus to the one obtained to the freedom factorizations.
Can you just go back to that last
Yes.
slide? I was just looking
Yeah.
at your G plus factorization there. So you've got branch points at plus or minus B over Qi or something.
Yeah.
How does that work out?
The
So you've got
you are saying
Bottom left term.
yeah,
bottom left
top right, you have these square root functions. So
here, okay. No, this is it's not alpha inside the square root.
It is in the other expression, or am I misreading? Is that an A instead of an L?
Here?
Sorry.
A, yes, it's A. A, it's not alpha. So sorry, the symbols are very similar, and they are very small also. No, we don't have branch. Here is the comparison of one component, the component 1, 2 of the matrix factorized, and you see overlap on the real axis of alpha and the relative error. In this case, we have also a rough discretization, A equal 20, H equals 0.1. To finish my talk, sorry for the late, the topic of freedom factorization will be more examined in the workshop with this presentation that is prepared by Professor Daniele, and I will give the talk. And here is a slide about solved problems in electromagnetic. Thank you.